In week C material, we are going to be solving systems of equations using determinants. So if you remember, back in week 4, we calculated the inverse of a matrix as A inverse equals 1 over the determinant of A times A adjoint. So we are going to essentially figure out how to do these calculations for matrices that are bigger than a 2 by 2. And then still, we can use that to find the solution of a system of equations as x equals A inverse times B. So all of this goes back to solving systems of equations. So now is our next method to use on top of the ones we learned in week B. So if you remember, these are our steps. If we want to find the inverse of a matrix, we need to first calculate the determinant to determine if the matrix is invertible or non-singular. So if the determinant of A equals 0, that means A is singular, it's not invertible, A inverse does not exist. So in MATLAB, if you do see the determinant equal to 0, it will say matrix is singular to working precision or something along those lines to indicate that the determinant of A equals 0. On the other side, if the determinant of A is not equal to 0, then A is invertible, it's non-singular, and we can go ahead and pursue like normal. For a 2 by 2, it's still the same thing. It's still these values minus those values. So the main diagonal minus the other diagonal. For anything bigger than a 2 by 2, we can go ahead and calculate the determinant using what's called cofactor expansion. So what we're going to do is we're going to go ahead and pick a row or column. In our matrix. So we pick one row or one column, doesn't matter which row, does not matter which column, we will always get the same answer for our determinant if we follow these procedures. And we can do cofactor expansion along that row or column. So before we get to cofactor expansion, we need to know what in the world a cofactor is. A cofactor is a signed determinant. So a cofactor itself is a determinant. So in order to calculate the determinant, we need to go ahead and find more smaller determinants. And we're going to do this by removing rows and columns from our matrix and then changing the sign on our answers based on this grid here. So if we want to find the cofactor for an element, finding cofactor Cij, so which row and column, we're going to go ahead and remove that row and that column from the matrix, calculate the determinant of the remaining values, and then adjust the sign according to the grid. So for example, if I want to find cofactor 2, 3, so row 2, column 3, so the cofactor corresponding to this one here, I'm going to go ahead and remove the row, remove the column that element is in. So I remove that row, remove that column. What that's going to give me are remaining values. So 0, 1, 2, -2, the remaining elements in my matrix. Then I'm going to go ahead and find the determinant of this. So find the determinant of this matrix. And then I want to go ahead, once I find the determinant of that matrix, I'm going to go ahead and go to my grid here and find the sign of this corresponding location. So the grid always starts, you don't have to have the grid written down on the side. It always starts with positive, negative, positive, and then it alternates going down and going over. So if I get to this element here, that means I have a negative, so I'm going to change my sign. So this is how I calculate the cofactor of C32, the cofactor of the element in the second row, third column. So if I do that, it's going to be negative 0 times -2 minus 1 times 2, or negative 0 minus 2, -2. That is my cofactor for this element right here. Then I can go ahead, erase all this fun stuff around it, and I can go ahead and go find another cofactor. So if I want to find cofactor 1, 2, so this element here, I'm going to remove the row, remove the column it's in, write down my remaining element, so 0, 2, 1, -3, and then adjust my sign if needed. Plus, minus, that's a minus. So this cofactor would be negative 0 minus 2. This one would also be, it would be positive 2. Oh, this one would be positive 2. My bad. Whoops. And there we go. That's how we find cofactors. So every element in a matrix has a cofactor. So how can we use cofactors to find the determinant? We can use cofactor expansion. We're going to pick a row or a column. Doesn't matter which row, doesn't matter which column, pick a row, pick a column. Find the corresponding cofactors for all the elements in the row or column. Then what we're going to do is we're going to multiply the element in the column by its corresponding cofactor and add them all up together. So for example, if I want to find the determinant of this matrix over here, I can pick any row, pick any column. Let's pick this column here. So I would go ahead, I would say my determinant of A equals element A12 times C12 plus A22 times C22 plus A23 times C23. Where I take A21, which is 2, times its cofactor, find its cofactor, plus A22, which is also 2, times its cofactor, plus A23, which is this -2 here, times its cofactor. Add them all up, and that's your determinant. And like I said, it doesn't matter which row or which column you use. You can use any one. You will always get the same answer. If I use column 2, I will get the determinant. If I use column or row 1, I will get the same determinant. So in general, we want to pick the row or the column with the most zeros. So if I pick column 1 here, then it's going to be 0 plus 0 plus 1 times its cofactor. So it's the least amount of work. But regardless, I will go ahead and I will find the determinant for that matrix. So here's what it looks like mathematically. Cofactor expansion along a row, cofactor expansion along a column, same idea. And that works for any size matrix. For a 2x2, we obviously know how to do it. For a 3x3, there is an alternative method. It only works for a 3x3. It cannot be done for any other size matrix. So we can call this a shortcut method, not necessarily, but it is another method we can use for a 3x3. And sometimes I like to use it, sometimes I don't. It just depends on how many calculations I'm going to have to do. But in order to use this method, we're going to go ahead and write the matrix next to itself. So I copied over these values to here. Write the matrix next to itself. Then we're going to multiply along the main diagonals. So the main diagonals being the ones here, I'll highlight them in green. In green. The main diagonals are these ones. So go along my first diagonal here. Multiply these together. Multiply these together. Multiply these together. Add them all up. That's what this demonstrates right here. Then I'm going to go ahead and do the same thing on my other diagonals. So I'll do that in blue. These are my other diagonals. So multiply these numbers together, multiply these numbers together, multiply these numbers together, add them up. So that's what this represents over here. Once I have done that, then I need to go ahead and take these diagonals minus these diagonals. So kind of like how we did it with a 2x2, but now we have more diagonals to add and multiply together. So these diagonals minus those diagonals. It's kind of like a modified fish, which is what I call the 2x2 method. So for this matrix over here, it would look like this. I would copy the values next to itself. And then I would multiply these numbers. So I'd get 0. Multiply these numbers plus 2. Multiply these numbers plus 0. That's my first set of diagonals. Then minus my other diagonals. Multiply these numbers, 0. Multiply these numbers, 0. Multiply these numbers, 4. Subtract the 2. So it'd be 2 minus 4. My determinant here is -2. So for some matrices, it's really easy to do this shortcut method. For some matrices, it isn't. It really just depends on your preference. You should know how to do both, cofactor expansion and the shortcut method. But note, the shortcut method only works for 3x3 matrices. Okay, so that's how we go ahead and calculate the determinant of any size matrix using cofactor expansion, or if we have a 3x3, we can use this second method. There are quite a few properties of the determinant. So the determinant of the transpose is the same as the original matrix. The determinant of the inverse matrix is 1 over the determinant of the regular matrix. There's a couple things that tell us whether or not we might have determinants of 0. So if any 2 rows or columns are the same, then the determinant is 0. If all of the rows or all of the columns are 0, then the determinant will be 0. If I have 2 matrices that are multiplied by each other, the determinant will be their determinants multiplied by each other. And we will explore these properties in class because we'll see them show up a couple times. If we have a triangle matrix, so a matrix with only elements along the diagonal, then the determinant, so these can be whatever, then the determinant is just going to be the diagonal multiplied by this diagonal, which you can see with a 3x3 with the shortcut method. And then lastly, the last 3 properties are what happens when we apply row operations to a matrix. How does our determinant change? Okay. If we multiply a row by a constant, then our determinant is also multiplied by that constant. That's what this shows. If we swap 2 rows, then my determinant changes sign. And that makes sense because if you look at the cofactor grid, note to swap these 2 rows, you essentially change the sign. And then if we do a strict elimination step by saying Rn equals Rn plus some multiple of Rm, note the coefficient in front of Rn here is 1. We don't multiply row 1, or the row we're replacing, with a constant. Then our determinant does not change. So all of these are properties of the determinant. We will do an activity in class to investigate these properties. So once we find the determinant, then step number 2 to find the inverse is finding the adjoint matrix. For a 2x2, we had these 2 switch places, and these 2 change their sign. That's how we find the adjoint of a 2x2 matrix. For any other size matrix, then the adjoint is the transpose of the matrix of cofactors. So if A looks like this, then I just find my corresponding cofactors. So find the cofactor corresponding to A11. That becomes C11. Find the cofactor for A12. That becomes C12. Find the cofactors for all the elements in my matrix and then transpose it. So that means this row becomes this column. This row becomes this column. This row becomes this column. And that is my adjoint matrix. It's just the cofactors for all the elements transposed. So for a 3x3, this is actually a really nice way to find the inverse. For a 4x4, then it becomes a little bit more complicated. But this is a great method for finding the inverse. A inverse equals 1 over the determinant of A times A adjoint. Where really it relies on understanding how to find a cofactor. Once we have A inverse, then X equals A inverse times B. There we go. We have the solution. So that's another method that we can use to solve a system of equations. Find the inverse of A, calculate its determinant by using cofactor expansion, pick a row, pick a column, find all the cofactors for the elements in that row or column, multiply the cofactor by its element, add them all up, get the determinant. Find the adjoint matrix, find any remaining cofactors, put them in a matrix, transpose it. A inverse equals 1 over the determinant of A times A adjoint. Multiply that by B in order to go ahead and get your solution. The second method for week C is something called Cramer's rule. It also uses determinants. And it turns out if the determinant of A is not equal to 0, so note this only works if the determinant of A is not equal to 0, if it's non-singular, if it's invertible, then our solution becomes essentially determinants and determinants and determinants, where our first unknown equals a determinant of a matrix called A1 over the determinant of A. Our second unknown is the determinant of a matrix called A2 divided by the determinant of A. And then we would continue for as many unknowns as we have. The determinant of our third unknown, our third unknown is equal to the determinant of a matrix called A3 divided by the determinant of A. Where A sub k, A sub 1, A sub 2, A sub 3, is a special matrix where the kth column is replaced by the B vector of the system. So if I had a 2x2 system that looks like this, I would have two unknowns, where x1 is going to be the determinant of A1 over the determinant of A. Where A1 here is A, where the 1th column, the first column, is replaced by my B values. So this is B. Then I would go ahead and find the determinant of this matrix and divide that by the determinant of A. If I want to find x2, I would take the determinant of A2 over the determinant of A, where A2 is going to be my A matrix, where the second column is replaced by B. So in order to solve this system of equations with two unknowns, I would only need to calculate three determinants. If you have three unknowns, you would need four determinants. Determinant of A1, determinant of A2, determinant of A3, and determinant of A. If you had four unknowns, you would need five determinants. So if you want to solve a system using Cramer's rule, calculate the determinant of A. In A, replace the first column with B to find A1, find that determinant. Replace column 2 with B to find A2, find that determinant. Replace the third column in A with B, find the determinant of that matrix. Find the determinant of A. So this becomes a relatively simple method. It's useful. It doesn't work very well for all systems of equations, but it does work well for when it does work, which is a weird way to say things. But all we need to do is just calculate a bunch of determinants. Then we can go ahead and find our solutions. This also allows us to find one solution or one unknown at a time. So if I'm only interested in finding x3, all I need to do is find the determinant of A3, divide that by the determinant of A. So I only need two determinants. Okay, and that is all the material. We'll go over lots of examples in class, and I will see you guys then.